And so now a considerable number of configurations were simulated. I want to show you how my screen looks like during the experiment or during the optimization here. As you can see here, we have the Octopus, where you can stop or pause. I always put it here, like I hide it from my screen so that not to click on stop or pause by mistake. Because you can still use your work space, you can still use your computer or your laptop while the simulation is running or the optimization is running. So here I will stop the optimization and leave this last one. And here, as I have showed you before, we have the C, where I will find the YouTube. Here I can find simulated configurations. I have 19 simulated configurations, and I have also the images here. But as you can see, the images is not accurate, and you need to fix them so that you could get a good images for the simulation. However, I don't mind this because I will show you how to bring the configuration, each configuration for each simulation into your Rhino so that you could render it or take it into your research or your work generally. So here you can see we have the forms number values of the forms, dynamic parameters, in addition to the windows and the depth of the shading devices in the southern direction. So here I will close this and check. This is the last simulated one. As I told you before, we need to change this into a white background because actually you might get a major review if you have a gray background, because it makes your model not look clear. So you need to have clear figures in your presentation or in your paper, whatever. Here I have the background. I will choose the solid color and choose the white. And here I can also use the rendered one instead. And we don't need the grid anymore because we have modeled our building, so there's no need to have it. So here I will go to the display options. Again, in the use application settings, I will use the white color. Here it's okay. Now it's fine. You can see your model in a good way. So here we have this pipe, and this one I might increase the radius of the pipe to show it in a good, in a better way. So now we will get back to our as I told you before, you can here save first. You can save your document because this will save the data inside Octopus. And also this one was saved before, so no need to save it again. So here I will click here. And as I told you, it's a single objective optimization. So you will be able to find just two arrows, one for the total thermal load and one for the genetic diversity, which we don't need actually to deal with. So I will choose here from navigation, and I would bring this one so that I could see my all the results in a good way. Here you have something which is called cube view, and you can zoom on click. This makes you view or navigate through your windows here in a better way in the user interface of the Octopus. And here you can see if you hovered over one of your iterations or boxes that are, each box represents one iteration. If you hover over it, you can see here in this part, you can see the dynamic load, the total thermal load, and you will see also the genetic diversity, which we don't consider that much. So this is 2.6. You can also mark preferred. You can use it to mark your configurations. So we have here two values. Mark this only also, sorry. This is, as you can see, the total thermal load is 27,000, and here the total thermal load is 26, which, as you can see, this one is the optimal result in this simulation or in this optimization, because actually we have run the specific number of configurations, and these configurations are not enough for sure. If you are doing a research, you need to run a considerable number of configurations. For example, you might run like 5 generations. You might reach thousands of iterations. You might reach more than 10,000 and so on, or you might reach 5,000 or 1,000, as you can see, according to your experiment. And here I will hover over this and click on it, and then reinstate solution, so that I could see the solution in my in Rhino. This might take some time according to your computer resources and according to the simplicity of and complexity of the experiment. And here you can see it reinstated, and now we have a total of 351. Here when you hover over the total thermal load, you can see that the unit is kilowatt hour. And if you want to know the unit for the energy use intensity, it's a kilowatt hour per meter square. So here, as you can see, you can also you will find that your dynamic parameters are adjusted to the value of the values that corresponds to this configuration. So reinstate solution changes the sliders and changes also, and it reperform the simulation. But at this stage, you know which is the best and which is the worst solution that you have. So now I will go here to the font size in this Ladybug Legend parameters, and I will change it to make it more smaller, so that we could see it clearly in our in Rhino Grasshopper. You might also change the position of your perspective, so that you could take better and clearer image or figure. And here for the north, there is here we have the north. I might change the point so that I could bring it here. I will put here a point and then set 1 point. So here I have a better perspective to print, or I might also take print screen, and that's it. It's going to be clear. You can just copy or print screen and then place it into your Photoshop or your Word file. So now I will change the colors. I will no more use the visualization for our energy or thermal energy results, but rather I will use this one. So we need here to turn this into false, because each time you're going to change your model or adjust it, the simulation will start, because once you change anything in your model, the simulation starts all over again. So I will just turn this into false, and I might use something else to use this decompose honeybee by type to visualize my model in a better way. So I might use the gray for the walls, and I might change here this into a blue or dark blue so that it could represent the windows. I might use also brighter color for the walls. And then here we can remove this. And also we need to visualize the ceiling. I will use a white color for the ceiling and for the roofs. The ground floor, it's not necessarily because we don't see it. So here we will start now doing the simulation for daylighting. So the first thing is the component which is called run daylight simulation. Here you can see that we have a honeybee objects. So we need to bring this honeybee object from the component honeybee set energy plus zone construction, which is the last component we have used in creating or modeling our energy models. So here I will hook it up in the honeybee objects. It's important to note that honeybee run daylight simulation does not account for the shading devices. So I need to bring the shading devices from here, from the honeybee context, and to hook them up in the honeybee objects. And here we have set that we might not have shading devices, but this may cause problems. So we might just, but it's okay. It's okay. I'm just saying because we don't have here, we have nothing here, but it's okay. It's okay to have no shading devices during the experiment and to have some time in a time one or whatever value for the shading devices and to have zero in other times. So here, the analysis recipe, which we will see now, it's called the Honeybee Annual Daylight Simulation. And it has the EPW weather file that we have chosen before to be in London. And then it has the test points, which will be located in the above the floor of each space. And we have the PTS vectors test mesh and the RAD parameters. And here in RAD parameters, we will use the default available in Honeybee RAD parameters. And I will show you now, I will also disconnect this so that you could see the floor and the sizes of the mesh, but here we will have a problem, so I will just hook it up again and disconnect the roof, the windows maybe, and the walls also, because we need to see what is gonna happen in each floor. So now we have taken another one, which is decompose by type, and we will set the floors, expose the floors in case we have ones. We don't have exposed floors in this case. We have ground floors, so we will hook it up. So here we have the grid size. In this case, we want to minimize the calculation time, and I'm just showing you what is going to happen here. So I will change it into 3, for example, but it's recommended that you use minimum 2. The grid size is the distance between the testing points, and here the distance base surface, which where are you going to place the test points in this case. And then I will set this also into true. I will do solution and recompute so that it could work. Sometimes we have problems due to issues with the Grasshopper itself. So I turned on this one, true, but it didn't run because here the shading devices, because shading devices will run in a good way in the energy simulation if you don't have a shading devices, which means you have a 0 value for all this into 1 and 2, for example, and then set OK. Now the simulation runs in a good way. And here you will see 3 windows, as you can see here. As I told you before, the simulation, the daylighting simulation takes much more time. So I will stop again the record and then get back to you when it finishes. So now the simulation is finished, and we have. So now the simulation is finished, and we have values coming out of this metrics. So here, for example, if we hooked up for the daylight autonomy, we're going to see values which actually these values represent the number of dots that we decided here. We decided to have 5 grid size. So as I told you, we have for each 10 by 5 space, we have just two test points. So here you can see that we have the zones. Each zone has 2 values except for the core, which actually received 0 in both floors. So we have 0 here. So in order to work with this, with the values, these values coming out of what we have told before, read annual results, we will actually separate first separate data, use the separate data and hook it up here. Then we will get the number, which is the total 17 test points. We will here perform mass addition, which is 160. And in order to bring the total value or percentage of the daylight autonomy, we will divide the total number by the number of the test points that we can find from here. We have the test points coming out from here. So I hooked it up to list length in order to know the length of this, and then I will do perform mass addition. Know that I have 18 test points, total of 18 test points. So it's going to be divided here, and you will have the daylight autonomy percentage, which is 8.8. Again, here in useful daylight autonomy, useful daylight illuminance, you can do the same thing. That's separate data, mass addition, and here you know that from this list that you have 18 points, and here automatically it's going to be divided by the number of test points. The total value will be divided by the number of the test points in order to give you the useful daylight illuminance percentage during the year. So now we have here the number, which is useful daylight illuminance, 100 to 2000. And here we have also the daylight autonomy. We want to perform a multi-objective optimization instead of doing single objective. Now we will do multi-objective optimization. We will connect these objectives along with the energy simulation, the thermal energy performance, or the value for thermal energy performance. And here you can double click you can see that it started to give you. I will reset, and now I can see that I have the daylight autonomy and useful daylight illuminance. So an important question that I get is that why I cannot see the thermal energy performance in the name here in Octopus. It's not working. No, it's working. But the problem is that in this case, in Grasshopper, now the hooked up value or component does not contain number. If you connect it to a panel, it doesn't contain number. So once you run the simulation for thermal energy in addition to the daylighting, you will find a result. So now I will start running the simulation for for the thermal energy, so that I get a value for this number. So now I have a value here in the number. So again, I will double click on the octopus and I will reset. So we now have values in all dynamic parameters. As you can see here, I have a value in the thermal energy performance. I have also values for both daylight autonomy and useful daylight illuminance. Now I will double click again and reset. And as you can see here, we have the total thermal load, the DLA and the UDI. And I will also add diversity parameters as a fourth objective. And as I told you before, you can adjust these issues, or just leave them like what they are at the default settings. And then I will start the simulation, or I will start running the multi-objective optimization, and then get back to you when it finishes a considerable number of configurations. So now I will stop the optimization from here. And I need to wait so that the computer or the laptop works again. So again, we will look back into the TT toolbox. In case you want to record the data during the optimization, you can use the TT toolbox, and here we will add the extra 2 objectives available here. So I will add here plus 2 and hook up this one as DLA and hook up this one as the UDI, and here I'm going to eliminate this. And you will need to set this again into true. Well, when you choose to set it into true, everything that was recorded before or saved before in the C file will be override. So you need to copy and paste it in another position so that you do not lose your data. So I want to mention that an important note that Octopus only minimize the objective functions. So that's why in this case, you can see that the value of the DLA and the UDI was multiplied by -1. So that it could be when Octopus minimizes these values, then we will go to reach the highest value. And so here I will double click, and as you can see here, we have the useful daylight illuminance, we have the daylight autonomy, and the total thermal load. And here I will use the cam or orthographic and the camera, and here I can see that the total thermal load, I can bring the minimum one, which is in this position in terms of total thermal load. The minimum one is 25312, and the maximum one is maybe 36. So this is the minimum one. So I might mark this one, and again I will. You can reset your camera, and then I will use orthographic again. And here I will bring this side so I can see the daylight autonomy. Here is the optimal result in terms of daylight autonomy. So I might use again the camera and reset it so I can see here. This is the value that has again. I will get this down so that I could see the values for the daylight here. As I hover over one, I can see that the total thermal load, and I can see it's DL. So here I want to get the optimal result in terms of DLA. So I will check this one and then use orthographic. And here, this one is supposed to be the optimal result. Again, I will. And again here, this one is for the DLA, which is which had the value of the value for the DLA is 14.1. So here, this is 12.7. So this is the one that we couldn't actually select before because Octopus is not working in smoothly, so you need to do some tricks and trials so that you could select what you need to select, and so that you could get the right graphs. So I will unmark this. Here we have the optimal solution in terms of total thermal load, and the optimal solution in terms of DLA, daylight autonomy. And here I need to bring the total solution, the optimal solution in terms of UDI, which should be in the bottom part. So in terms of UDI, it's going to be the same one. It's negative 13, which is 13.5 percentage. And as you can see here, this one is lower. It's a negative 12, which is 12. So we have here the optimal result for both is the same. So now we want to bring what is called the trade-off. We have the Pareto front solutions. Pareto front solutions actually are placed in the corner because the more we come to the corner, the more we get the best results, because actually we will have in the corner the lowest total thermal load, we will have also the highest daylight autonomy, and we will have the highest UDI. And as you can see in the daylight autonomy, the highest number is negative 14.17, which is what we have here. And also in terms of the useful daylight luminance, it's 13.5, the number here, and it's the same here. So you might find something in the corner. What is available in the corner is going to be the optimal solution. We should have a couple of, usually we have a couple of trade-offs, but in this, because we didn't run the simulation for a long time and we tested a very low number of configurations, we're having just we have one here, so I mark Gene, and then we will actually again make this axis view reset this axis view, because this actually stands in the corner as much as possible. You can see here we have 296 and we have 29690, 11% for the daylight autonomy and 12% for the useful daylight luminance. So now So let's now reinstate, for example, the trade-off. I will reinstate this solution, and actually all the simulations will start running. I want to do this. I want to run the simulations because I want to visualize the results in terms of thermal energy and daylighting. In case you don't want to visualize the results, you don't. There is no need to make the Boolean toggles turn it into true. You might turn off the Boolean toggles in the thermal energy simulation and in the daylighting. So we now will visualize the UDI. We have here analysis results, and I will hook up the UDI 102,000 here in the analysis result. And it shows the results regarding this. And I might also hook up, I will actually disconnect this and now visualize daylight autonomy instead. And that's here we are finished. I have showed you before how to visualize the thermal energy performance. So I hope you enjoyed these tutorials, and thank you for watching.